There's a fundamental exploit problem, which is how do you choose what data you're trained upon? It's quite clear that you just randomly pressing mashing keys on your keyboard won't get you very far in Minecraft. Having 20 eyes, I don't think there would be a concept. I think that would be a good, well-eyed agent, to be honest. Could come with some setup like this. It would be a bit strange. It would be like the cell that fights most is the least grandmother-like thing.
Hi everyone, this is Axel. This episode I have Beren Millidge with me. Beren did a PhD in machine learning and computational neuroscience at Edinburgh and is now a postdoc at Oxford. He's interested in the free energy principle, active inference, the exploration, exploitation, trade-off and reinforcement learning, and about 30 other things. If you're not familiar with those terms, don't worry, we'll unpack them throughout the episode. In the episode I also asked Beren some speculative questions about multimodal representation, shallow minima, autism and representation in the brain. We also talk about predictive coding, which came up in the previous episode with Mark Spivak. Then we explore whether something similar to backpropagation could exist in the brain, and discuss how the concept of time has been massively understudied in neuroscience and some of the temporal challenges the brain faces when it is involved in perception or memory in real time. At the end, Beren gives us some pretty good career advice on writing and publishing. As usual, if you want to skip ahead to any specific questions, there are timestamps in the description. Enjoy. Great to have you here, Beren. When did you first hear about active inference or predictive coding? Feel free to pick one of the two. And what were you doing at the time when you first heard about them?
I first heard about my master's program, which was a master's in AI at the University of Edinburgh. And I must admit, what I was doing is I was procrastinating after doing what I should have been doing. I started reading papers by Fixational, and I think I watched a few lectures by him on YouTube. And I think sort of what drew me to it is the interdisciplinarity and breadth of the FEP, and like the idea that you have these data which can actually explain so much about like the world and intelligence and these kinds of things, which is quite different from like a lot of machine learning, which is what I was studying, which is very focused on like very specific benchmarks and things, and doesn't really try and like deal with sort of fundamental questions as much.
Right. So let's talk about the free energy principle. And it's quite funny when you look at the Wikipedia page of the concept, there's like a sentence which says something along the lines of, this concept has been criticized for being so difficult to understand, even for experts. And that's quite funny, but also maybe a bit daunting. So I thought we could maybe break it down in steps to explore the concept. So maybe first you can give me sort of a non-science elevator pitch. Then we'll talk about some of the background concepts of the principle and a bit about reinforcement learning. And then I'll ask you to sort of explain it formally as someone would to like a science audience. So I'll start with question one. Imagine we're in an elevator. I'm 18 years old, have maybe a standard high school science background, and have no idea about AI or neuroscience. How would you explain your research to me? Go.
Okay, so I'm actually going to do slightly diverge from the question here. So I'm going to do two things. One, I'm going to explain the FEP in that context. And second, I will explain my research, which isn't entirely based on the FEP. So for the FEP, I would say that the FEP tries to understand what makes systems adaptive. If we have some like object or something and it's sort of surviving, like an animal and it's surviving, what are the most abstract fundamental properties it needs to be able to actually do this, to survive, to actually basically resist the fact that the outside world is constantly trying to kill it, essentially. And can we describe this process in an abstract mathematical way? And the FEP says that basically in order to adapt to the world, you need to be able to model the world. And the way to model and then respond to the world, and the way to describe both of these processes is through essentially inference. And we can talk more about what inference is and stuff later. But that's what I would say for the FEP. And so for my research, I would say I'm inspired sort of by this idea sort of at a very abstract level. And some of this research I have done sort of directly on FEP theory. But the other big thing I'm trying to really understand is how credit assignment and learning work in the brain. So essentially in the brain, you obviously have like billions of neurons, but only a few like sort of sensory surfaces, like you have your retina and your ears and your auditory and stuff. And basically most of these neurons in your brain are actually quite far away. They're like multiple links away from sort of actual direct contact with, the sensations and stuff. And so then the question is, how can these neurons, which are far away from their inputs, actually learn to predict their inputs and learn basically what they should be doing, how they should be firing in order to actually improve what your cognition is doing, how your cognition is functioning. And so that's the credit assignment problem, and that's what I also studied in neuroscience.
Awesome. So you just mentioned inference, and I'll ask you in a second to sort of explain what that means. But maybe also it's useful. This is sort of from a textbook, but there's a difference between standard decision making and action selection. Maybe you can sort of explain the difference between those two, and then also explain inference.
Okay. So I'm not sure. I mean, I would say action selection is decision making, really. I wouldn't think there's a difference between this. I'm intrigued actually. What would you say the difference is?
Well, in my mind, I kind of came across the textbook with Anosif and a few other people about action selection. The idea was that if you have decision making, you know your choices. So let's say it's like some paradigm where you have to choose a city, which one is larger. And whilst action selection is more in the sense that you don't really know what the options are, and you have to basically infer what the options are from sort of an unknown hidden environment, and then based off that inference you then have to choose which action to take. If that makes sense.
Okay, I see. Yeah. No, this makes sense. It's kind of okay. This makes sense. That's not how I think about it at all. Actually, that's interesting. So what you're describing as action selection is just kind of like meta action selection, right? It's like meta decision making, and that like you have to decide what things you want to actually decide about.
Well, how do you think about it?
Okay. I think that ultimately these are all kind of the same problem. What you're describing is sort of the meta style action selection. We don't actually know what the actions are. This basically comes back down to a sort of high level inference problem about you presumably have some model of like what are the possible actions that could exist, and you have some evidence like this is actually an action, this is not an action, and you need to take sort of exploratory. So we need to find out information about like what things are actually actions.
All right. Next question. Can you explain the Infomax principle and the principle of redundancy reduction? I suppose they're related.
Okay, yeah. So the Infomax principle is kind of to do with perception, and the idea is essentially that you have like some sort of observations of the world, and then you also have some sort of internal representations or states which are meant to sort of represent those observations. And the Infomax principle is basically that you want your internal representations to have as much information about the external world as possible. And so you can define and measure them. Is this information basically, and then you maximize that measure. And so redundancy minimization is kind of the opposite of this, but whereas basically redundancy minimization is more towards sort of efficiency of transmitting and representing information, which is essentially that you don't want to represent or transmit like redundant information. And so you kind of want to keep your representations as minimally redundant as possible while maintaining the most information about the external world. And so this is kind of like what efficient perception is.
Yeah, on the efficient perception point, maybe you can link that to evolution and how redundancy reduction is important there.
There's several levels of this question. I think in terms of sort of the sort of biological systems that have evolved, they'll both be extremely good at redundancy reduction and Infomax. Like if you think about vision, for instance, your retina and stuff is extremely good at extracting relevant parts of the visual scene and also making that redundant by subtracting out all the stuff that's actually very redundant. Imagine in your retina you have various not pixels, but bits of light close to each other are very likely to be very similar to each other, like in a scene. The retina can actually subtract out these differences and then only transmit the differences. And this is basically a very powerful form of redundancy minimization, in that lots of different bits of information which are almost the same are essentially all redundant, and it's the differences that matter. In your brain also you have all these adaptive filters and stuff which actually extract information which is very specifically relevant to you from the external environment. And so that's kind of like the Infomax, and that these filters are meant to be highly informative about the outside events. They're not just like your brain actually has a very precise picture of what's going on, even if it's highly compressed.
So you just mentioned the word states and actions, and I want to get into reinforcement learning. And besides states and actions, 3 other important terms are observations, policy, and a value function. And could you, using those 5 terms, sort of explain reinforcement learning really briefly?
Okay. So reinforcement learning is fundamentally the problem of some agent in some environment, and you receive observations from this environment, and you have to choose actions of basically you have to do stuff, and then you have to maximize some goal, which is usually thought of in terms of rewards. Like you want to get the most rewards possible. There's a big question of like sort of on the computational representational side how to do this. And so a policy is one way of thinking about it, and the policy is just you have some mapping between sort of states or observations and actions. Let's say if I'm going to say X, I do action Y. And then the goal is to optimize this policy in order to maximize reward. Another way of doing it, which is sort of complementary, is to think about things in terms of value functions, which essentially for each state, you assign like how much long-term reward am I expecting to get in this state. And then the problem becomes basically how to get to the states with the best value function.
Right. So it's also important about maximizing like reward over time, sort of the expected reward.
Yes, exactly. So the value function is the expected reward from now until the sort of end of time.
Next question. What is a Markov decision process?
Right. A Markov decision process is a mathematical abstraction of an environment. Basically, we assume for reasons of mathematical tractability that at the current state basically composes everything you need to know about the environment. And so basically the state of future times only depends on the state of the current time. And the state of the current time only depends on like the history one step back. So there's no like long-term temporal dependencies in this environment.
Right. What is the difference between model-free versus model-based reinforcement learning?
Okay, so model-based reinforcement learning, as it says, tries to learn an explicit model of the environment. And so essentially this is learning your MDP, aka you learn your state and you learn the transitions between states given actions. And then given this model, you can then basically simulate the environment and do sort of counterfactual simulations. You could say, if I try X, what will happen? Will this lead to high reward or not? And then basically do the things that give you high reward. Whereas model free essentially doesn't do this, but kind of defines everything implicitly. So essentially it's learning the policy and the value function directly, as opposed to simulating them through a model.
Awesome. So we have discussed 7 or 8 terms now. So I think now we can sort of get on free energy principle and active inference. Could you try to explain it to us?
Okay, so this is going to be boring. So returning to the previous thing about how essentially the free energy principle is all about sort of what does adaptivity and sort of survival in a challenging world mean and require. And basically the FEP states that essentially require systems to either implicitly or explicitly model their environments essentially. And this modeling can be shown to take place via essentially can be described as Bayesian inference. So various cool things are, one is that any kind of inference can also describe any action selection problem. And so basically you can think of action selection, aka decision making, as just an inference problem. You can also think of it the other way around, funny enough. You can think about inference as an action selection problem, which in the case of Bayesian inference is just kind of like the truth of your beliefs. To go the other way around, you can actually instead think about action selection as basically inference, but instead of optimizing for truth, you essentially define truth to be like value. You define truth to be reward, then you use the whole machinery of inference to actually do action selection this way instead. And so that's what sort of active inference is so that's the second term, is active inference. And all active inference is basically treating action selection within this framework of inference. So you just treat action selection as inference, hence active inference.
Okay. Can you explain the story a second time using the ideas of prediction error? Because I think that also explains it quite well.
Yeah, sure, I can do. So you can think about this maybe more concretely in terms of prediction error. So if you have, say, some beliefs, say for observation, you have some beliefs and then you actually get some data. And then if the data is different from your beliefs, then obviously something has gone wrong with your beliefs, we assume at the moment. And so basically this prediction error tells you how to update your beliefs so as to minimize the prediction error, right? So like if you believe X and what actually happened was Y, then maybe you should actually update your belief X more towards Y. So that's the inference side of things. And so the active inference side of things just reverses this and says, if you have data and beliefs, then instead you actually want to act on the data. And so you want to take your data more towards your beliefs rather than the other way around. And so this is basically how actions go into the world, in that they change the data that you see essentially to bring that in line with your beliefs by minimizing the prediction from the other way.
Exactly. So you're going to select the action that will minimize the prediction error as to confirm sort of the model
Exactly.
you already have.
Yes.
Right. I think at some point you mentioned exploration a bit, and let's talk about the exploitation dilemma. So this is often taught in reinforcement learning in textbooks with the multi-arm bandit problem. Can you sort of explain this dilemma to us, maybe using these examples, or if you have a different example in mind using that?
Yeah, I mean, sure. So the exploitation problem is really fundamental to essentially any situation where you have uncertainty or like lack of knowledge about the world. When you choose actions, obviously you receive observations, and this is new information. And so essentially, if you want to sort of maximize some long-term reward in the future, there is always this trade-off between doing what you know in the moment is good and works well, and sort of doing what will give you more information and then hopefully discover new things which might work even better. And so the multi-arm bandit problem is kind of a very basic sort of test bed of this. And so there you essentially have different like bandits, which were like gambling machines, I think, back in the day. And so these, dispense rewards with certain probabilities. The goal is obviously to find the bandit which, gives you the reward with the best probability. if you start out with, one bandage and it's pretty good, and then like you tried a few others and they were all rubbish, then the question is like, do you keep trying new bandits? And like, because they could well be rubbish, and they probably are rubbish. If there's one that's actually much better, then like you're obviously losing out by not finding it, but obviously there's the cost of trying all the necessary rubbish things first.
I'm not sure how much this is related to science, but my dad, when he like read a book about this once, he keeps on loving to make this point that, when you're young, you love to explore lots of things, and now that he's older, he loves to exploit what he knows is good for him. So I'm not sure that's a good sort of dynamic explanation, but
no, it's definitely a good one. The way I always like to think about this to make this concrete is actually in terms of like restaurants, in that like you might have one restaurant, you know exactly what you like there, and it's really good. But then like the question is like, is that actually the best restaurant in the whole world? And the answer to that is probably not. And so like there are probably other ones which are better, but like most of the restaurants you try randomly will be worse than the current best one, because you found that one and it's like say 95 top 5%. Say to get to one above top 5%, you have to try like 20 or so other ones first. And so is that trade-off really worthwhile? I've actually thought about the exact point that your dad was raising, and I think that's actually a combination of two things, right? One is the exploration, exploitation, and the second is the opportunity costs. As you get older and you have more experience, you obviously have much greater skills, and so not using this really good skills you have are much more costly than trying to go to learn new skills. Whereas if you're younger, you don't have any good skills really, and then like it's much less costly to keep exploring essentially.
Yeah, that makes sense. And on the restaurant point, I suppose there's also within each restaurant, then you can, how much do you explore the menu?
Yeah, exactly. Yeah, you definitely have like the meta. It's basically this hierarchical exploration form. Yes.
Yeah.
And then like even above restaurants, it's like, do you go to restaurants at all, or do you do something else? Life is nothing but exploration, exploitation forms.
So let's stick with that theme. In reinforcement learning, when one sort of tries to program an agent to either explore or exploit, one sort of has to program different distinct processes. If you model this as active inference in trying to minimize expected free energy, which is sort of a future way of looking at free energy, it sort of leads to both exploration and exploitation. And could you explain the intuition behind this?
And I don't think there's like a super amazingly clear intuition on this. What you really want to do is you want to minimize basically this quantity called the free energy, which I should probably explain actually. So how that relates to inference, because the whole thing is called the free energy principle. And I'm not even to have talked about that. So to backtrack, free energy is some mathematical measure of the discrepancy between essentially your beliefs and basically your sort of model of the data, which includes the data. And then expected free energy is meant to think about the sort of the free energy like over multiple time steps in the future. And so you're trying to think about what will happen to the free energy, if I do roll out various courses of action in the future. The sort of intuition really is that the expected free energy, because it's involved about rolling stuff out into the future, tries to include some kind of information about like which regions have high levels of uncertainty in. And then the assumption, which is not necessarily a good assumption, is that future space with high levels of uncertainty are where you should explore and go to. This isn't necessarily the case, right? Like there are some cases where this fails. So for instance, if there's random noise in some regions, expected free energy will try and explore there because it sees like, hey, I have extremely high uncertainty about this thing. But then that could be totally irrelevant to whatever you're trying to do, right? Like people don't just spend all day staring at like static TVs because that's very high uncertainty, but it's like useless. So like there's this thing about uncertainty, pure uncertainty itself is not that useful. Well, it's not always useful, but it is a good sort of heuristic to bias exploration. And that's what the expected free energy sort of includes.
Yeah, it's weird. I think we'll talk later about sort of the role of attention and in a top-down way. But the way I think about it is that, let's say I'm trying to read quite a difficult paper and I get distracted with sensory stimuli somewhere. And if to a certain extent, I don't know what sort of interpret it. So if it's sort of uncertain, then that might be a reason to look to it. But as you said, well, not it just being uncertain doesn't mean necessarily that I care in a sort of a motivational sense. So in a sense, it has to be uncertain, but also maybe related to sort of what I want to focus on. Yeah. So uncertainty within a scope of what could I get from this? What is the reward of the uncertainty?
Exactly, yeah. And in fact, there's sort of three levels of uncertainty. There's like motivational uncertainty. Then there's like actual, I guess, like modelable uncertainty. And so that, because it could be the fact, well, let's go the other way. So there's also like unmodelable uncertainty, which is like pure randomness. And so you might be very uncertain, about like the outcome of a bunch of coin flips, but like there's nothing that you can really learn from looking at a bunch of coin flips other than it's like purely random, you can't predict it. Whereas uncertainty in a lot of cases actually has components in that you can learn about if you go there. And so that's sort of the ideal solution to the exploitation problem is like this sort of learnable uncertainty. And then obviously that should also be weighted by essentially motivational affect, right? Like you should go to try and resolve the uncertainties that are A, resolvable in theory, and B, that you actually want to resolve.
Right. So you just mentioned the expected free energy, which is trying to predict how to minimize free energy in the future. And you have a paper called Deep Active Inference as Variational Policy Gradients, where you introduce an algorithm called Deep Active Inference. And this is sort of an improvement from something earlier called Tabular Active Inference. And what are the difference between the two, and how does this new one, is it better able to sort of represent the policy space in the future?
Right, sure. So that paper has sort of two advances over what was then the state of the art, really, in active inference. And so one is how the agent represents the world and sort of the state of the world. And so we talked before about how MDPs have a state, markup decision processes, MDPs. And previously in like most other active inference literature at that time, they basically were explicitly representing the state sort of in a discrete way. So they were saying like, there's like 5 states, and in each of these 5 states, I'm in state 1, 2, 3, 4, 5, and then, there's some explicit transition. So this requires a very discrete and explicit model of the environment. And so this is obviously very nice, but it doesn't really scale up to when you have agents, which actually have to do with very large environments. And so the first thing was utilizing all the work that's been done in deep reinforcement learning about essentially using neural networks to encode the state of a problem, and then using that as then your state, which you then can do reinforcement learning on. So that's the first thing. And the second thing in that paper was basically so active inference before that was very model based, in that there was explicitly a model of the environment, and you did inference essentially by like simulating forward in the environment and then figuring out what happens if you do X, what happens if you do Y, etc., all the way forward. And then you get this big tree. And then given this tree, you sort of evaluate the expected free energy for sort of each endpoint of the tree, like each sequence of actions you could do, and then say, I will just do the best one, or whatever. But like this is obviously very sort of in terms of computational complexity, this is very slow. It's like it could be exponential if you have a really big tree and don't prune it at all. What the second thing in this paper did is that it used the sort of model-free methods from deep reinforcement learning as well to actually apply to active inference. And so specifically, it showed that you could basically treat the expected free energy over the future like a value function, and then optimize it using the tools you use to optimize to learn value functions without having to explicitly simulate like an exponential tree of like all possible futures.
Okay, so in the same paper, you compare this active inference algorithm to Q-learning and actor critique on sort of a few benchmark tasks. And you found that the active inference did really well, which is like impressive. But what was interesting that we only talked about exploration, exploitation, and this is the idea that when you explore, you get not just the reward itself, but you maybe get something called an epistemic reward, which is basically a reward in an informational sense. And you found that randomly exploring within these tasks was enough, and you didn't have to explore sort of in a structured way where you actively look for epistemic reward. And your case was sort of to say that, well, maybe with the simple tasks, this is the case. But if you look at more complex tasks with maybe like hierarchical compositional structures and long-term dependencies, maybe just random exploration doesn't work, as is usually done in reinforcement learning. And do you have some sort of an example of how such a complex task might look like?
Yeah, so returning to, I mean, basically these complex tasks will be the kind of things people have to do in like daily life, or like actually complex or video game style environments. Classic one, which is now like at the frontier of reinforcement learning, is Minecraft. And so can you train an agent to play Minecraft? It's quite clear that you just randomly mashing keys on your keyboard won't get you very far in Minecraft. And really, it probably won't get you anything good to happen, because the way reinforcement learning works is it needs essentially a reward gradient. And so you basically need mashing your keys randomly, must do something good with some reasonable probability. And then once it sort of latches onto that, it knows, now I mash this key more often and this key less often. And then it sort of can build up from there. But like the key issue is basically when you have very sparse rewards, so like it's really hard to get any reward. And if you're just randomly twitching in the corner, you're unlikely to do that. Then you basically need these kinds of exploration stuff. And in that paper, we're using very simple benchmarks from OpenAI Gym. They're kind of tough to do for a human, which is funny because they're basically like controlling, physical objects and stuff with like keys. And so sometimes, if you have like 6 dimensions of movement, that's hard for a person to keep control of. In terms of the actual reward gradients, they're always quite straightforward. And like if you move a bit to the left, that's actually good and you'll get a slight reward for doing that. And so those are actually quite easily solvable with sort of these model-free techniques which don't require much exploration. But if you go to these harder tasks, and we actually showed this in our later paper, the reinforcement learning through active inference, which we actually showed the exploration bonus does actually help in these cases. And if this is something I've been wanting to do for a while, but I went on to do other things, is try and scale these up even further to like these kind of more harder tasks, like some Atari, like there's some games in Atari where you really need exploration and stuff like Minecraft. But like I think that's future work at the moment to see. But like it's a big question in sort of standard reinforcement learning, not just active inference as well, is how, what are the best ways to get this exploration working? What sort of objectives actually work best for exploration? What sort of architectures do we need? These kinds of things.
Yeah, in my mind, Minecraft is definitely has like long-term dependencies, but it's still quite very in the AI world in the sense that you learn based off games. Have you seen any work which comes from like other disciplines where you try to sort of model a complex task based off, I don't know, inspiration from psychology or something similar?
Yeah, no, I mean, a lot of stuff in exploration also comes from sort of psychology experiments where they have put like mice in mazes and stuff, right? And so to me, this is both an exploration and a memory task, essentially. And you also need to first explore the maze and then remember the maze. There's definitely lots of work, including in sort of in the active inference literature, about how active inference agents do these memory tasks. Sort of in the sound active inference, you have a very clear model of the environment and sort of this and you get basically epistemic bonuses, which allow you to go and explore things that are useful. You can do all these kinds of cool experiments where you like basically give the mice, or whatever in the maze certain cues and say like, if you go here, we will reveal to you, which way is best or something. And this kind of and you can develop all these hierarchical cue schemes and then look at like compare, the behavior of the agent, which simulates this and is sensitive to these sort of epistemic contingencies against like what actual mice or stuff do, right? Or people do if you make this into a video game maze. And so there's like lots of sort of work on this area as well, like trying to use these as actual testing grounds to see what actually real people do.
Yeah, that sounds really interesting. I think that this nicely bridges to the sort of, the theme of the podcast about like embodiment with the mice, but also I've got a question about multimodal representation. And this is all a bit like speculative. So if I say something stupid, please correct me. But so I was listening to a podcast interview with Carl Friston, and he was comparing deep learning models with active inference models. And sort of his point was that deep learning models tend to overfit more, and active inference models don't do that so often because they try to reduce complexity, redundancy, so like try to make perception more efficient, as we talked about earlier. And his case is that was sort of these deep learning models might have like very sharp minima for gradient descent. The active inference models will have like a very shallow scene with lots of shallow minima. And they might be better at generalizing across tasks because of this. And I was just thinking whether, besides comparing deep learning with active inference, whether it's just about how much multimodal input you get. Because I don't know, if you have, let's say, just one modal dimension, let's say vision, and you have an image classification network that looks at dogs and cats pictures, I think it's quite easy in my mind to like, I mean, I don't know how the network is doing it, but in my mind, it's easier to get stuck when you sort of try to compare, I don't know, a wolf to a dog, and then you have like a very specific, maybe overfit representation of what a dog is. Well, if you have sort of a multimodal embodied interpretation of what a dog is, where you, I don't know, maybe link it to semantic features of, did I see the dog in the forest? Did I see it with an owner, etc.? Then the minima are closer to each other and maybe more shallow, and the multimodal representation can maybe bridge the minima. And I'm not sure whether any of this makes sense, but do you have a thought about this?
Yeah, no, I mean, this makes sense. I think there's several aspects in here which need disentangling, really. So one is that at the moment, everyone is having huge success with like large-scale unsupervised deep networks, mostly multimodal, sort of extremely large-scale tasks, right? Like you have the GPTs and your DALL-Es, whatever. And these are obviously extremely good at like very wide and very large amounts of data. And it's not necessarily multimodal, but that will be there in like a few years. It's very big. It's very, very varied within one modality, right? Like it's like all the text on the internet sort of style. And like that's much bigger than like dogs versus cats. The points about the shallow minima, I am not completely sure about. Personally, I think that these networks empirically do learn very shallow minima, but I think this is basically due to their massive degree of over-parameterization. So obviously these networks are extremely large and therefore have an insanely massive parameter space. And so the more parameters you have to play with, the shallower your minima get. Well, they're not really shallow, but you basically have these huge surfaces of optimality where like moving in, say a third of the dimensions basically will still be optimal. It will make no difference because you have so many parameters to play with. And so this naturally will lead to much sharper minima and potentially better sort of generalization performance, although like there's a lot of theoretical research into why these massive overparameter ones don't massively overfit. And so that's still kind of an open question, but it is fundamentally to do with like basically this kind of fact that you have like vast amounts of optimality everywhere. And so it's quite easy to reach them. And if you start in a good sort of prior position, you're likely to not find some overfitting solution. So that's one thing. The second thing is about sort of the active inference models Carl is talking about versus the deep learning. And so this is really essentially to do with the degree of structure in the solution. And so Carl is very sort of big on thinking about like how to try and actually get more structure imposed into the problem. So he thinks essentially that if you can encode neural networks with specific kinds of structure, and then these networks do inference with that kind of structure, then they should basically learn better representations than networks which don't have any structure, like a standard deep neural network, but like learns from a lot of data. And so whether this is true or not is debated in the field. And I think it sort of both is and isn't true. In that I think it is true for a given amount of data and for a given size that any given structure will outperform like a lack of structure. But it's also not true in that like if you can produce neural networks at a much greater scale, then these can actually perform comparably to a much smaller and more structured one, essentially. Basically, that's the trade-off. Knowledge of structure versus compute cost is basically, and like memory size and all this sort of stuff, is my thinking about that. But also, obviously, if you have cases where data is limited, then basically it's much more important to make the most of the data you have. And so the trade-off tilts more towards the structured side. Whereas like if your data is basically unlimited because you're scraping the whole internet for text, then like it's probably much better to go towards the compute side.
I've got one more like quite speculative question. So I was going to ask you about maybe like connecting explore versus exploit to my point about multimodal representation. But as you said, maybe the shallow minima are more the result of the number of parameters. And does having the like active inference models where you consider explore and exploit, how does that relate to the number of parameters and how shallow the minima are?
Yeah, so this is a really good question, right? So basically, the explore-exploit doesn't really apply to the sort of supervised learning style tasks. Well, unsupervised video. You have some data set and you're learning some loss function, and the data set is fixed, basically. There's no, and this is how like GPT and stuff is trained, right? And there's basically no explore-exploit problem there because there's no issue with selecting data. The data is just given. And then there's no like actions as such, right? And so basically that's just essentially finding some optimal parameter set for this. And so for reinforcement learning, the problem is different. And obviously they do get exploit problems. And I think kind of the question you're asking really is to do with essentially the epistemic, sort of the model uncertainty, in that there's a fundamental exploit problem, which is essentially how do you choose what data you're trained upon. And so, and you're right, this does depend on the sort of architecture and ultimately the sort of shape of the loss landscape, right? In that if you have a shallow minima, then maybe it's easier to traverse across that, so you need less data. But on the other hand, it means that your gradients will actually be quite small because the slope is quite low. And so maybe you need more. And I haven't actually thought a great deal about this. But you're right in that you probably do get sort of benefits of scaling in that like the more scaling you have, the less data, because your model has more capacity, the less sort of exploratory data you need to be able to infer anything new. But then you still need to be able to actually figure out what data you need. But I mean, that might, well, I don't know really. I don't have a good intuition about what will actually emerge or naturally as behavior of these things scale. And like, there hasn't been much work really, or at least like well-known research in like scaling of, so publicly released research in the scaling of like model-free and model-based reinforcement learning compared to obviously the scaling of like language models and stuff. Personally, I suspect DeepMind have quite a good idea because they do lots of scaling and reinforcement learning. But like, I don't think there's like a huge amount of open research on this. Well, there's been published and stuff. So I think it's a really interesting question, like to what extent exploit can be solved by just scaling up versus its fundamental difficulty in the problem.
Okay, awesome. Let's go back to, we were talking about the brain and like modular function. And during your master's, you did some work on autism spectrum disorder, and there were some findings in the literature that people with autism might have less long-range underconnectivity of networks, of neurons, and more local overconnectivity. Well, what was that work about, and does it to link to what we have been just talking about?
Yes, that's a good question. I must admit, I did this work a long time ago. A bit hazy on the actual details. There's definitely something to be said about that overconnectivity of the brain. And so this is something brain has, which large-scale deep networks don't really have, is they have this pattern of basically this small world connectivity pattern. where essentially they have lots of local connectivity and then like a few large-scale regional connectivity. And so this is kind of different from your networks that basically have uniform connectivity patterns across the whole thing, typically in some feed-forward architecture. And so in that sense, no real long-range connectivity between layers, say. So, I mean, I think there's something there. I think it's worth thinking about like what sort of inductive biases this kind of small world structure gives you. And I think they could be beneficial. I think especially having long-range connectivity like this could be beneficial.
I think maybe for listeners who are less aware with the neuroscience or the AI side of things, but let's say maybe like a psychologist who has to diagnose people with autism, what kind of behavior with autism would you maybe like relate to this under connectivity, long range, and local over connectivity? So there's like a behavioral intuition about this.
Yeah, I mean, so the work on my master's was built off some really interesting papers, which I must admit I've forgotten the name of now, which deal with this. And they're basically arguing that essentially this long-range connectivity is to do with the sort of equilibrium between different regions of the brain. This results in basically people on autism being like hyper-focused on small-scale things, well, not small-scale, but hyper-focused on specific things and not being able to take like integrate the sort of global context and take that into account, which would be presumably communicated by these sort of long-range connections. That's a very heuristic story, although it makes some sense to me intuitively, and that's why I sort of looked into it for the master's thesis. And I think this sort of fits obviously with what we know about autism as well, like extreme like sort of micro focus and then like lack of large-scale details, which would make sense with the connectivity pattern.
Okay, awesome. We talked about active critique earlier, and some other RL models called control-less inference. They often have sort of a separation between the generative model of the environment, so like, well, how do you model the world, and the goals of the agent. And in active inference, the generative model, to quote you, is contaminated with value imbuing biases. So in a way, the generative model and the value functions are integrated. And I found this was super interesting. And maybe you can say a bit about that and also maybe link it to evolution and enactivism.
Yeah, sure. I think this point about like the generative model being involved with biases versus being like the true generative model is really sort of philosophical distinction to me. And I used to think differently when I wrote this paper. So basically, what is happening is that you can either think about inference, sort of this active selection by inference as two things. So for normal inference, you basically don't have this problem because your value is truth, right? You want to optimize for truth and get, basically find truth. But like obviously for reinforcement learning, active inference style, you actually want to achieve some specific goal and not just find truth. And so then the question comes in, how do you interact finding your goal with sort of actually needing to understand the world and needing to also find truth, right? And so basically, there are two ways to do this. One is that you can consider yourself as building some true model, and then given this true model, only optimize for value, right? And so the second thing you can do is basically combine them together. And so build a model that is trying to be true, but is also trying to optimize for value. And so this is actually the same thing, essentially, but like it philosophically makes a slight difference. You can either think of this as first, from like a computational perspective, you can think about it like first have a model, the model predicts what's really going to happen, it's going to predict lots of different things, and then you choose your actions basically, you find the thing find the best prediction basically, or you can have it that your model is actually predicting basically what it's the best thing that it wants to happen, and then the action selection problem is actually figuring out how to take actions to make that best prediction actually come true, essentially. And so these are kind of two sides of the same coin, really.
Okay, I know you have also cited in some of your papers philosophical work of like Andy Clark and others, and maybe can you link this to enactivism, or there's this idea of radical predictive processing, which like consists of conservative predictive processing, if that rings a bell?
Yeah, sure. Yeah, no, definitely. Yeah, I can. Yeah, so basically, this philosophical distinction is very correlated with what people think about like the goal of perception and representation and these kinds of questions. Some people, who think that like the goal of perception is truth, basically to do inference. And then once you find truth, you can actually then, optimize for value given your true model, right? So this is the first thing I described. And this is basically what most people in like machine learning AI think. And this is because it comes from the sort of, basically the AI community in like the 70s, the 80s, sort of computational and also connectivist, but sort of the computational like logic theory people, right? And so then your goal is to find truth, and then with truth, you can figure out what to do. Whereas the sort of an activist of ecological psychology comes from a different community, which is often based in sort of psychology at that time. and sort of is related to this, Gibsonian. I don't know if you know about Gibson, but this Gibsonian idea of like, which I think has an awful lot of merit, is that like perception is not just like to find truth. Perception is for a specific point, right? Like, if you're an organism, you don't necessarily care about the truth of things. You care about like surviving, doing well, and reproducing, whatever evolution wants you to do. And so basically perception, the only goal of perception is to actually do action selection. It's not like there's no like reason you should necessarily want a completely true world model. And so this is where this difference comes down to. And basically the question is like, do you need to have an intermediate step of true representations which you then optimize? Or can you just have a direct shortcut of like value-biased representations is the question. Personally, I think that the brain has some, so from a neuroscience perspective, my own perspective, I think, because I'm a bit of a compromising person, that I think there is a combination of both, in that you need, obviously there's some bias towards like stuff that values you. Like you care more about building a world model about things that you actually value, right? Like you don't spend ages, well, most people don't spend ages like investigating weird random nuances and stuff, which is totally relevant to like life tour. But like also the value of having a true world model comes with like long-term generalizability. And then like if you find out true things about the world, they will stay true, even if like what you need at this moment changes. And so in that sense, you basically get more generalizability at the cost of like less immediate sort of reward. And so because of this generalizability, I think like the early stages of processing are heavily biased basically towards truth. And this computation is also simple, right? Because basically it means you have a bit of your architecture which only need to care about like local sort of true values, like predicting what's going on locally, without needing some sort of global broadcast of like what I want to do at this precise moment. Whereas other bits obviously need to do this. And so then I think like later stages of processing, by like, as you say, like explicit attention to our mechanisms are biased more towards value than towards truth.
Awesome. So this is sort of a two-step follow-up question. So on the enactivism scale, some people like disagree on the point of representation in the brain. How is there representation? How much is there?
Yeah.
Well, in predictive coding, it's often like seen as like, are there like probability distributions? And then you just mentioned James Gibson. I was wondering on the point of how these representations might look like. James Gibson has this concept of affordances, of thinking about, as you said, not that the world as in a true sense, but sort of what we can act upon. And how looking forward, I realize these are two very different questions, but how looking forward, is it better to basically think of these representations in the brain as representations of affordances, and therefore we should think about evolutionary niche representation versus how much should we think about representations in the brain as modeling representations in the world as they are, how basically our understanding of statistics has to be either biased by the world or like an evolutionary niche statistics.
Yeah, I mean, so this is a very good question. I mean, if I did have an answer to this, I'd be very happy. But like, and a lot of philosophers would be looking for one. But I think that really, to me, I disagree that this is like some huge fundamental question between like affordances and representations. To me, affordances are representations. They're specific kind of representations. And I think that obviously representations should be biased towards what you do with the representations. And like, well, it's a natural fact. In any architecture, the representations that it learns will obviously depend on like how it learns and like what it's actually optimized to do. And so I think definitely it's I think like the visual cortex and stuff primarily represents like true representations around the world, which at least like are basically compressed versions of the outside. But then other regions of the brain, like I think obviously like the striatum and the basal ganglia, which involves an action selection, represents the world in basically this affordance sense, right? And they probably get affordances from the cortex and stuff like this. So basically the real question is, what are the representations which will make it most easy to express the required computations and outcomes that are needed by the system? And so these will differ depending on what you need the system to do. To go back to a later point, an early point about are there representations at all, which there's also a lot of debate about. I also think that this is kind of like essentially an interpretational question, for some very basic systems like feedback loops, people will say there's no representation in the feedback loop, it just has some dynamic. And so at this point, I think representations are fundamentally an interpretational quantity, in that you can interpret the feedback loop as having representations of like error and stuff. Like in your PID control, you have like an error, which is the difference between the set point and the actual value. And this isn't actually instantiated anywhere, but it must exist implicitly in the dynamics. And in this sense, it is a representation. But I also think that like basically the reason you need explicit representations, which are not implicit, not interpretational, is basically for sort of communication between regions, and that you basically need to compress information down to small amounts of information to transmit it places. And that's when you need basically an explicit representation, or like an explicit code for specific things in the world, which cannot just be implicitly transmitted through dynamics.
I like that nuance. I was talking to Mark Spivak in the last episode, and we talked about, he sort of made this point that a lot of issues about whether people attribute computation to a rock or a wall, it's just how you interpret it. And I guess with your point about like feedback loops, then not thinking of representations as this is the thing, but sort of in a, I guess in a functional sense of the representation is used to do that as, let's say, compressing information. Then it takes away interpretability by not looking at what it is representing, but what is the functional reason it is representing something for. Okay, right. So you just mentioned the visual cortex, and I want to get onto predictive coding, which you have written a lot about in the last 2 years. And I think your work on fixational eye movements might be like a nice way to introduce this. So what are fixational eye movements and what is visual fading?
Okay, so this is a kind of niche and very interesting to me topic. So basically, fixational eye movements are like when you're just staring still at something, your eyes are constantly making these tiny little jittery movements around. And so this differs from like normal saccades when you actually explicitly look somewhere different. Then your eyes make a huge jump, but even when they're not saccading, they make basically these tiny micro saccades, which are like very small, and like you don't have any sort of conscious awareness of them in the same way you do have conscious awareness of saccades. And so that was about fixation. What was the second part of that question?
What is visual fading?
Visual fading. So basically, if you actually suppress, well, you can't suppress microsaccades, but what you can do is you can basically move the sort of, put people in this environment where basically you move what they see and track their saccades. So what they see is basically precisely following the saccades, and basically this exactly counteracts the microsaccades. And in this case, people will slowly become unable to see anything. So basically, they will see the visual world slowly fading out of conscious perception. This is something, I don't know if you've ever had this experience actually, but you can do yourself if you like go close. If you like go close and stare at like some patterned wallpaper for a long period of time, you will often find like the actual patterns will appear to fade. You need to be like somewhat close, but like not too far away. And you will actually, I don't know if you've ever had that experience, but like you can get that. And like that's another example of visual fading, where like especially regular patterns will fade out basically.
Okay, I'll try that after the episode. That sounds fun. How does this relate to predictive processing, predictive coding?
Yeah, sure. So basically, the idea behind why this happens is that what you're seeing, what the retina is transmitting, is prediction errors, and this is for reasons of redundancy, like we discussed before. So, like most of the visual scene that you see is highly redundant, and basically your brain doesn't want to, or your retina doesn't want to transmit all this information. So, it essentially only transmits prediction errors up to the brain, and then the brain, given these prediction errors, then reconstructs conscious awareness of this highly redundant scene. But if what goes on your retina is basically still, and then it's highly predictable, and so all of it gets predicted, and so basically you don't get any information sent back up, and hence you don't see anything. And so this is basically what predictive coding would predict, right? That if you have no prediction errors, you don't see anything. And so because you have a perfect model.
So in the same paper, you make the point that these fixational eye movements might help with like creating robust and spatial invariant representations of a scene. So could you say a bit more about that?
Yeah, sure. I mean, this is I just want to preface this is like a speculative point I think I made in the discussion. And so I'm not claiming this is necessarily the case. But my argument is basically that you have these tiny eye movements. These eye movements will basically create images obviously on your retina of like slight perturbations of the object, and specifically slightly different viewing angles. And so this kind of having a bunch of slightly different viewing angles is actually good for making the brain learn about like things like depth perception stuff which require slightly different angles, and also some sense of essentially like object permanence, and the objects are not like flat things, they're three-dimensional objects. And secondly, this is something that was actually big when I read this in like 2018, but has now I think fallen out of favor, is that there used to be this thing called data augmentation in machine learning, where you would have some data set, but it was quite small. And so you would kind of create a large data set to train on by like doing different perturbations on the data set, which didn't change the identity. Like in a classification, if you slightly moved around the dog in your image, it's still a dog. So it should still be classified as a dog. That gives you more data to train on. And so this was found to increase the robustness and accuracy and stuff of the method. And now people basically get around that by having so much data, they don't need to do data augmentation. In fact, they have too much data. I don't think this is true of the brain. So I think the brain still probably needs to do data augmentation. because it can only receive, one retinal image per like whatever microsecond, whatever. And so it can't like scrape the entire internet instantly. It's probably still another slight mechanism which it uses to sort of build, in case you get more slightly different data and build up a slightly better model of the world than it otherwise could.
Yeah, this episode is not out yet, but I recorded an episode with Felix Hill from DeepMind, who looks at like grounded language models.
Okay.
He made this interesting point that when you have a multimodal agent learning in a 3D simulation, so it has visual input of its room and it has language mappings of like, looks at an object and it's told this object is, I don't know, this. His intuition was that this was better at learning the representations in sort of a retrieval sense than some image classifier who had only one snapshot of an object, because it could look at the same object from several different angles at several different timestamps. And that seems similar to the story about saccadic eye movements, looking at the same thing over different like little angles and then adding those together. And I was thinking that for people like Felix who do that sort of work, do you think that you could train these agents to implement something like fixational eye movements, or is something like data augmentation enough and then you can sort of adapt it to like have the biological plausibility of the fixational eye movements? Could that help with like multimodal learning?
I think that it could. I think data augmentation is probably going to work for that. But like, I think one thing that could, which I wanted to implement in the reinforcement learning paradigm for agents which I haven't, is actually having binocular agents, so they have two eyes, right, which give them a slightly different perspective on the scene. And so this is not what people do in reinforcement learning at all. They just present like a stream of images, right, and that's like the visual input. But in fact, I think it actually helps humans a lot for depth perception, various understanding of the 3D world, to have this binocular input constantly. And then you can see that as you move around in the environment, how both your eyes change and stuff. And so I think that would be something worthwhile to look into in reinforcement learning.
Yeah, I've been recently like looking around and seeing animals. I've been wondering, how is it if you don't have frontal eyes? So like birds who have like eyes to the side, I guess they have less depth perception. It'd be interesting to see, how does object recognition, I mean, it'll differ for different reasons as well, but how does it differ just because of that?
Yeah, no, that's a really good question. There's a bunch of stuff like predators usually have close together eyes, right? Because basically they need this highly precise depth perception. Whereas like if you're sort of like a prey animal, you don't need precise depth perception. You just need to know like there's something coming, like get away. And
exactly.
So like there's definitely like an evolution sort of, because there's a clear trade-off, right? Like close together eyes, depth perception is good, but field of view is bad, right? And so then the other trade-off is field of view is good, but depth perception is bad. Definitely interesting trade-offs to be had here. But on the other hand, like in reinforcement learning, there are no trade-offs, right? You can give your agent as many eyes as you want. So it's like you could have kind of all sorts of fun with that.
Yeah, I mean, I wonder, when you say there are no trade-offs at all, I wonder, as you said, it'll make qualitative difference whether you have like 1, 2 eye or 20 eyes. And do you think then, well, reinforcement learning agent with 20 eyes lack? Like what would the consequence of that be, if you can speculate?
Yeah, I mean, I don't think that for having 20 eyes, I don't think there would be a consequence. I think that would be a good, well-eyed agent, to be honest. Like the trade-off would be needing like extra computations to actually deal with the inputs from all of these eyes, right? Computation simulated AIs don't have any of the same trade-offs as biological creatures, right? Because they're not having to hunt foods to manage to upkeep all their 20 eyes in the same way that, like animals are. So they're running off, Google's cloud budget, which is fine.
Let's go from predictive coding to precision. In the paper where you mentioned visual fading, you make this point that if someone pays more attention to, let's say, details of your stimuli, when visual fading normally would incur, you can prevent it by looking at the details. And the idea sort of that, well, as you increase the precision of the sensory stimuli you're looking at, then therefore you receive more prediction errors because you're looking at it in more detail, and therefore you don't get visual fading. Could you maybe say a bit more about this?
Yeah, I mean, you pretty much explained the mechanism there. The idea of precision is essentially a way to weight the prediction errors. And so like the higher precision, the more bigger precision weighted prediction errors become. So then if you identify that with visual fading, then obviously that will result in less fading, right?
On the review paper about predictive coding, you also go back to precision, and you make this point about how precision can also be modulated by top-down attention. And if I was a researcher looking into that and maybe working from the visual fading example or totally from a different angle, like how would I look at precision and top-down attention from like a research program perspective?
Yeah, so that's an interesting question. So I would say that there's actually quite a big sort of difference in the way we talk about precision and how attention is actually implemented. So in the predictive coding sort of mathematical theory, the precision is basically related to the variance of your input data. And so basically the idea is that this is a way to modify how much different parts of data affect your beliefs. And so if you have highly variable data, then you shouldn't really base your beliefs on it. You should base your beliefs more heavily weighted towards like data which isn't actually variable, right? There has been also people who identify precision predictive coding with sort of top-down attention mechanisms. So I actually disagree generally with this framing. I don't think the precision predictive coding doesn't serve the same purpose as sort of top-down attention in the cortex. You can make some equivalence by saying top-down attention weight stuff, precision weight stuff, and therefore they're the same. But like I think they actually serve different purposes. In terms of how to think about top-down precision, which is upweighting computations that you think are valuable or relevant as a long-term goal, which is how I view like top-down attention. This top-down attention should be much coarser grained than precisions which are very fine-grained, right? The precisions like for each neuron, the input to this neuron, is it highly variable, is it not? Whereas top-down attention is much more like coarse-grained, and it's like, is this sort of region of computation something I care about? Is these kind of broad-scale things something I care about? Does that make sense?
Yeah, I think so. So we have like an example of me looking at a visual scene and me looking at a specific area, then that area would be seen as maybe, well, the opposite of precision is variance, right? So
yes.
if I found that area more varied, would for that reason I pay less attention to it, or?
Yeah, so this is the other interaction with the epistemic seeking, right? So precision is kind of anti-epistemic bonuses, and basically, if something is highly variable, you should pay less attention to it. Whereas so when reinforcement, exploitation, that's like the opposite, right? And if something is highly variable, maybe you should pay attention to it. There's a bunch of interesting trade-offs here between like when should you pay attention to certain things and when shouldn't you. Precision, because it's assuming a sort of static world where you can't interact with the world, you just see data basically, and you want to form beliefs about that data. Then there's no exploratory component essentially, because you can't go and actually like explore things. You can just sort of receive data. And so in that sense, it makes sense to try and downweight data, which is basically really hard to understand, because like it's just going to mess you up if it's like highly random. But obviously, if you can actually interact with the sort of randomness, and you do think there's something interesting going on there, then you should probably apply the epistemics with bonuses and go towards the highly variable data.
Yeah, in my mind, this goes back to the value imbued generative model.
Yeah.
That if I look at something and there's like a top-down attention bias to look at because it might be useful, then, well, maybe the generative model, because if it has high precision, then I take something concrete away, like I can, exploit looking at it. And maybe even if there's variance which would motivate epistemic exploratory behavior, maybe the generative model can override that by making it seem less varied than it is, if that makes sense.
Yeah, no, that makes sense. I definitely think that there will be multiple mechanisms for upweighting and downweighting things according to their value. Because even for epistemics, like you need to determine when you want to explore and when you want to exploit. And so that there's like global scale parameters which affect this. Like if you're kind of happy with what's going on now, you're probably not going to explore. Whereas if you're really unhappy, then you're really going to explore. And so like there's all these kind of different trade-offs that need to be made. I think precision in terms of like the variance thing, like look to upweight things with the high precision, downweight things with low precision, aka upweight things with low variance, downweight things with high variance. I think like this is sort of a baseline mechanism, which is kind of going on all the time, but like it's sort of designed to be overridden in different circumstances.
So for the next question, I was gonna ask you about precision and dopamine, but so I sent you these questions in advance, and on the email exchange, you sort of pointed out to me that my understanding of kind of conflated sensory prediction error with reward prediction error, and the sort of the story of dopamine being correlates when you have reward prediction error and related to those subcortical regions, that's not necessarily the same story as it is for sensory prediction error, which is sort of more your field. And could you say a bit more about this distinction and what the two kind of prediction error types are?
Well, I would say actually I also ironically studied the dopamine as well. This is speculative, right? So like this is my opinion on how the brain works, is that broadly you have the cortex, and so it's a neocortex, and most of this is doing like unsupervised world modeling, which is based on sensory prediction errors. And then for the subcortex, obviously you have bits of it, such as the basic ganglia, which involved heavily in the reward. And so this is basically dealing with actual selection at a low level. And so from our thing, this is like heavily based on not like what is true, but sort of what is like rewarding, basically. There's also a difference in that both have like word prediction errors versus sensory prediction errors, but I think that the way these prediction errors are treated computationally is slightly different. So basically, the word prediction errors are not specific. Sensory prediction errors are very specific to specific sensations. So they're like, and very high dimensional. So essentially, they're like, you predicted this pixel, but you were wrong. This pixel is something else. Whereas the word prediction error is very low dimensional. And so it's much harder to learn from, essentially. And if you could learn from it, it would be amazing. The word prediction error is like, you messed up at some point in maybe the last like second, if you're lucky, or maybe like the last year. This kind of thing is very hard to actually learn from and like this highly precise way. And so instead, there's like a whole bunch of other algorithms, which are essentially model-free RL algorithms, value function learning, temporal difference learning, policy grading methods. These kind of things can learn to utilize this kind of very slow information, basically, this very slow and imprecise information to optimize towards improving reward. Whereas I think the cortex actually has a much higher bandwidth of information because it's much easier, because reward is ultimately a very long-term thing to evaluate. Am I doing okay in life or whatever? Like this is formed over many sort of like lots of time, right? And like you don't get a reward often for quite a long time after what already happened, right? Whereas am I currently predicting this pixel correct is sort of very, very rapid thing with huge amounts of information. My feeling is that doing sort of model-free RL without any of the cortical information is like really slow and kind of bad because the information you get is so slow and so like low dimensional. And so basically you use the high dimensional world modeling of the cortex, which is based sort of not based on reward, but based on like just truth essentially. Like can I build a true model of the world? That's high dimension, so that can happen rapidly. And you can have a really, really big and really good model based solely on supervised learning. And then it's just kind of guided by the sort of low dimensional, slow reward signals. That's how I think about it. These kind of prediction errors are therefore treated quite differently in the brain.
Okay, so if then the reward prediction errors map onto the value imbued part of the generative model and the sensory prediction error to the generative model part, then how they interact, there's a clash of dimensionality because you mentioned that reward prediction is lower dimensionality. And then on that point, you also mentioned timescales of, well, a reward is really hard. Like you have to think about it over time. And these are just things I'm saying. I'm not sure what I have a question right now, but I want to still ask two questions about predictive coding in the brain. I think we talked about sparsity at some point earlier. Predictive coding deals primarily like with layers where everything is fully connected, whilst sparse cortical connectivity is the idea that you only have very few neurons are active at the same time to model how sparse rewards and sensory stimuli are in the world. And how can you sort of reconcile this aspect of predictive coding with this well understood concept?
Yeah, that's a good question. And so I think really the answer to this relies on this sort of basically predictive coding is fundamentally like a model. And we're currently choosing to model fully connected architectures to get things similar to machine learning. Predictive coding can also be applied to sparse architectures, like there's no barrier to doing that. And it's actually very straightforward, right? Because any dense architecture can be made sparse by just zeroing out a whole bunch of the connections. Predictive coding can also model sparse architectures, and I think in the brain, obviously, it is in reality sparse predictive coding. The real question is that we know the brain is sparse. Current machine learning logical neural networks are not sparse, and they do really well. Sparse networks don't do very well. And so there's a big question here is why this is the case. Why do we not find sparse networks actually being as good as dense networks, so useful for various things? What are the computational properties of sparsity that are useful, and like what are obviously the ones that are not useful? Obviously, presumably, there is some kind of trade-off, right? Like sparse networks are good at some things, dense networks are good at some other things. And then the question is like, what is this trade-off? Why is the brain where it is on this trade-off curve? My feeling is that the brain will probably be more sparse than is optimal because connectivity costs energy and sending spikes costs energy. And so it's going to try and reduce that as much as possible. And so that may move it naturally towards a more sparse solution that will be optimal. But on the other hand, some degree of sparsity is also probably good, right? And so the question is trying to figure out what that is. And what is it about sparsity that is helpful? This is another thing I'm kind of interested in. I've been thinking about for a while. This is orthogonal to predictive coding. So predictive coding can basically work on sparse architectures as well as on dense architectures. It's kind of like a sort of algorithm. It's not like, it doesn't relate to the architecture. The reason we did predictive coding on dense architectures is because what everyone uses. It's what everyone uses because it works. And so then the question is, why doesn't the sparse one work?
In my mind, that the brain is so sparse and maybe like less sparse and optimal seems not necessarily like optimal in terms of, well, what is it trying to do, but maybe most realistic in how evolution plays out. Let's say with adaptation, networks change, then the change might not have an adaptive value. But if it's so sparse that the change only is a slight energy increase for the brain, so from 20 watts to 20.00001, well, then that might as well happen by chance. And then that's likely to happen a couple of times, hence, if that makes sense.
Yeah, exactly. So okay, so yeah, you have some good points here. So one is that I just want to clarify about optimal. When I said the brain is, suboptimal, that's optimal regarding like machine learning accuracy performance of the network. Not the brain, I think, is nearly optimal on its actual trade-off on its Pareto frontier of like energy versus accuracy. But obviously, that's going to be worse than only maximizing accuracy, which I'll talk about. So the other point, I agree, there is some level of sparsity, which is optimal, and obviously slight deviations around this level don't really matter that much because it would just be like a few neurons flying or whatever. But then obviously large deviations add up, and so there's probably some region where the brain could vary. This is basically the selection that evolution can optimize on. Some people will randomly be slightly more sparse, some people will be less sparse, and evolution can then obviously optimize that variability. Yeah, I agree. So there's basically two different sets of questions here. One is, what is the trade-off frontier of sparsity versus cost? And then the other one is, what is sparsity actually good at? And so we know there are large differences in sparsity even within different brain regions. Cortex is quite sparse, say 99% sparse or something, which is pretty sparse. You have regions, like the cerebellum, which are vastly more sparse, they're 1 in 10,000, say, sparse. This is obviously not to do with saving energy. There are some tasks which the cerebellum is really good at and specialized for, which requires high sparsity, and other tasks which the cortex is good and specialized at, which requires less sparsity. And so then the question is what are the different tasks and why is sparsity fundamental to their architecture such that they have evolved so different sparsity regimes?
Yeah, I really like the point about how some regions might be more sparse and some less. And I suppose that's also an evolutionary hyperparameter of which regions do you want to make sparse. In my mind, that makes ecological niche construction where animals suddenly adapt super quickly to changes in the environment. So it fits with that because it focuses on then the sparsity sort of as a way of accelerating which areas the brains increase connectivity. They can massively help that organism in that new environment, whilst then can maybe give up some other high connectivity for sparsity where that ecological niche isn't there anymore.
Yeah, exactly. Yes, definitely. There's very interesting stuff about different regions, have different sparsity characteristics. And some animals have obviously evolved completely different regions of the brain to deal with different senses. For instance, there's these fish which can sense electric fields. And so because of this, and they use it to catch prey, right? They detect prey and stuff moving in the field. And because of this, they have to have a whole new brain region, like the electrosensory field cortex, tries to deal with this weird input. This ends up being highly sparse. This ends up being a cerebellum-like structure. And so there's something about processing electrosensory field input that is really well suited to a sparse architecture. Whereas other inputs, visual inputs, don't seem to be. Olfaction is another one that is highly sparse, the input. And that's also a highly conserved circuit. So sort of outer cortex in your brain is actually very similar to what's in fruit flies and stuff. It's the same sort of circuit over and over again. So this circuit is obviously extremely highly optimized for olfaction, and it is a sparse circuit. And then the question why is the sparsity so good for some things, and then in vision it doesn't seem to be good. Vision has almost no sparsity. Well, it has the very minimal levels of sparsity in it. And so the retina is obviously pretty dense, LVN is dense, and then the cortex becomes normal cortex sparsity. And so there's something about the structure of the inputs and stuff that makes different levels of sparsity, different architecture essentially, better or worse, beyond the normal trade-off about sparsity is cheaper essentially. And so there's two levels of questions there.
I have to say, I barely ever read about sparsity, but now I really want to. This is really interesting. So I've got a question about negative prediction errors, which is the idea that, you could have positive prediction errors. You're not predicting something in the environment and then it comes up, and that's a positive prediction error. And you predict something and then it doesn't come up, and that's a negative prediction error. You make this point in the review paper that in neural networks, you can just model negative prediction errors with negative firing rates, but something like that couldn't exist in the brain. And you sort of go through some hypotheses of how the brain could do this. And one idea is sort of just having separate populations for negative and positive prediction error neurons. But the other ones is this idea that you could have cells which encode in antagonistic fashion, and that's similar to cells in the retina. And could you maybe talk us through the second solution?
Yeah, sure. So it's a different way of interpreting the first solution. Imagine instead of saying we have a light cell, and then a light cell has this negative firing rate, which is when it's less light than expected. Instead, you have a light cell and a dark cell. And so the light cell fires more, the more light it is, the dark cell fires more, the more dark it is. So difference in these cells will give you some understanding of the light level. And this is how color is encoded in your retina. You have different cones. You have like red cones, blue cones, green cones. And then you have other cells which form these antagonistic relations. You have like a red-blue cone, like antagonistic combination stuff. And this is why people, see the color the way they do. The idea here is that if everything is encoded antagonistically, which is a big if, and I don't actually believe, but as a thought experiment, if everything is encoded antagonistically, you can actually represent negative prediction errors in, say, one side of it will be encoded as positive prediction errors in the other side. So, for instance, if you have like a negative light prediction error, that's to say basically use a positive dark prediction error. That makes sense. So that's how you can encode negative prediction errors.
Yeah, it's really interesting. When I was reading it about the antagonistic way of it, I just sort of got all philosophy and was thinking, well, what if all perception has to be dualistic in a way? And I'm talking yin and yang thoughts. And I was just thinking, what if this is the case for most neurons, the way they encode the world? And do you have an example of what, well, maybe like an abstract thought could be like, which illustrates this duality in how the neurons could encode it? I'm not sure if that's...
Yeah, no, I mean, it's an interesting case, actually. I'm not sure. I end up being quite practical. I'm not sure to what extent this antagonistic coding could work. I think you could definitely have it, right? You basically have each neuron would need like an antagonistic anti-neuron. There are some bits of space, there are some sort of concepts which naturally fall into dual categories, and so antagonistic coding is easy. And then there are other ones which are much harder. To go to the classic sort of grandmother cell example, you have like, a cell which fires when you have your grandmother, and then therefore you would need a cell that fires when you don't see your grandmother, the anti-grandmother or something. It could come with some setup like this. It would be a bit strange. It would be like the cell that fires most to the least like grandmother-like thing. And you could definitely have a setup like this. You can actually train it as well. It's just an interesting thing to have, like, because some things are naturally antagonistic, other things not so much.
Yeah, the anti-grandmother cell. I like that. That's great. Okay, let's talk about backpropagation in the brain. So there's this, let's call it old story of why there used to be a consensus that something similar to backpropagation can occur in the brain. What is this old story?
Backprop has several properties which render it quite difficult to potentially, which don't seem to match with how computation in the brain works. And so essentially these are properties like locality. We think computation in the brain is mostly local, but backprop is not really local, and it requires you to propagate information all the way back through the output, from the end of your network all the way to the front. Basically, so that's the main one, and then there's some issues with like sequential stepping. So backprop computes the output, then one layer back from the output, two layers back from the output sequentially. And so we don't think the brain does this. Like you can't just see something and freeze and then require your brain neurons to go sequentially backwards from like somewhere. Like this is a strange thing to do. And then there's some minor issues which are like to do with like weight transport and stuff, and the actual computation of the algorithm require basically information to be duplicated in various places. The question is like, how do you do this duplication and actually make sure that like things stay in sync essentially?
Let's talk about some of those limitations in a second, but you got a paper called Predictive Coding Approximates Backpropagation Along Arbitrary Computation Graphs. And that's sort of a fancy way of saying that you created a predictive coding network that can implement anything from like CNN and RNN or like any form of neural network. And could you tell us a bit about this work?
Yeah, I mean, we basically solved it there. So what we do is we can define, like, given the computation graph of some neural network, you can define a predicted coding version of the computation graph, which is adding like prediction error units everywhere. So for every node, there's a prediction error node. And then what you can show is that, under certain assumptions, if you run this predicted coding network to equilibrium, and then basically do weight updates at the equilibrium, then the weight update you'll get will be very similar to the backprop ones. So the reason this is useful is that predicted coding doesn't have the same issues as backprop. It doesn't have the sequential issue because you're basically running all your neurons all the time. And so you have like everything converges like in parallel as opposed to needing sequential steps. And it still has weight transport issues, but that can be solved. So that can also be solved in backprop to be fair. That can be solved quite straightforwardly. And then obviously the locality of predicted coding is also local. And basically the mechanism by which this works is that during the sort of parallel convergence phase to equilibrium is essentially propagating the same information backwards as sequential stepping backward does, but it basically does it in parallel. So information slowly sort of trickles back during convergence to equilibrium, as opposed to need like a bunch of control cycles to be like, now this layer updates, now this layer updates, that sort of thing.
I'll ask you about the weight transport problem in a second, but in the paper you mentioned that with these predictive coding networks that they'd be a lot better if you had neuromorphic hardware.
Yes.
Do you have any of that right now? Like, do you have access to that? Because that's pretty cool, but I guess quite new and expensive, or Is that something
Yeah,
you're looking at?
It's something we're looking at, but various sort of theoretical stage. So we don't actually have access to any specific neuromorphic hardware at the moment. We've been looking into this and trying to understand, how we could actually implement these kind of networks on neuromorphic hardware. The main thing is basically that this inference phase I was talking about, the sort of convergence equilibrium. On a computer, this is slow to simulate because you basically have to simulate this convergence. So you have to simulate like a time t, now it's here, time t, it's t plus 1, it's here, and so forth. And basically integrate a bunch of differential equations. And so this is slow. But on an analog sort of circuitry or like any kind of neuromorphic hardware, you can basically set up the hardware such that the physics basically does this convergence of ODEs quickly. Because if there's one thing physics is good at, it's solving ODEs. That inference phase, which is like the majority of the cost, very quickly. And so that would be the argument for that.
Awesome. Let's get on to the weight transport problem. And I think you sort of mentioned, but it's this idea that axons are unidirectional, so it goes one way. It seems implausible that you can have forward predictions and then backward prediction errors through the same unidirectional axons. And what are some of the solutions that sort of could overcome these problems, and how could this exist in the brain?
Yeah, sure. So the solutions all come about by trying to have a backwards propagation pass, right, but not using the same axons. And so essentially, there are two ways to do this. One is you just have random axons, and so you don't even try and learn anything on the backwards pass. This was invented by Tim Lillicrap in 2016. It's called random feedback alignment. And so this kind of works. And so you can actually train neural networks in this way, but it doesn't really scale super well because we have this random backwards pass. And so it loses information every sort of pass gets sent through. And so the alternative is basically find some biologically plausible way to learn these backwards weights so that they become equivalent to the forward weights, but without needing a huge amount of transfer like across. You don't want to constantly having to calibrate the backward weights with the forward weights. You kind of want them to be independent, but kept roughly in sync. And so there's been a bunch of algorithms which actually can do this. There's a bunch of papers on this. So I actually wrote a paper not on this, on various things, but including this. I actually don't really think personally the weight transport problem is a huge problem. Quite easy to find heavy and sort of learning rules, aka learning rules that could be implemented in synapses, which can actually keep the forward and backward weights in sync, as long as sort of the neurons also have access to roughly the same information. So you can't have a completely spatially separated forward and backwards pass. But as long as the backwards pass, the backwards connections are kind of roughly talking to the same neurons as the forward connections, then this is possible. And this makes sense, right? Because the forward weights are learned using local information. And if that same local information is also available for backward weights, then you can also learn backward weights. Then the question is how to make sure that the forward and backward weights don't necessarily interfere with each other is the thing. Whether that's actually a problem we need to solve at all.
Yeah, in my mind, it seems like we're closer to finding solutions of how could you find the learning rules, but we're further away from the sort of experimental psychology evidence. At some point you make this point that if there were perfectly parallel structures where for each prediction forwards axon connections you'd have backward prediction error connections, then you would sort of see the structure really easily if you did any sort of analysis in the brain. And that it's not so clear because the brain is really recursive and so complex, so we don't really understand yet. And I also was thinking the role of long range connections to subcortical regions. I think you mentioned the striatum. All of that, how do you reconcile this issue of, well, we're not really finding these perfect parallel connections, but there could be other explanations for how it works.
Yeah, so I don't think there are perfectly parallel connections. There is a lot of evidence for roughly symmetrical connections, though, in that if some region protects another region, most of it gets protected back. And so the difference here is stuff to subcortical regions. And so then there's just, the cortex will protect the striatum, but striatum won't protect back to cortex. Instead, there will be some loop going through the thalamus and stuff. I think cortex to striatum is not involved in backprop. There is some other mechanism necessary for learning. It's basically in the subcortical areas. I'm not saying it's necessarily the same as backprop. I don't think the cortex uses the same algorithm as backprop. But I do think that there is some sort of algorithm with similar properties to backprop, aka it provides precise feedback to each neuron in implemented in the cortex. And I think there is a fair amount of symmetric connectivity. I think the recurrent connectivity is involved in being able to simulate recurrent stuff. This is another thing that backprop, neural networks don't really do time very well. People invent, there's obviously RNNs and LSTMs and stuff. This is not what people use much in practice anymore. And especially now the transformers have taken over. And transformers' main sort of innovation is getting rid of time. And it's so in that sense, they're kind of a step back from the recurrence perspective. I think there's some recurrence involved in needing to simulate, understand temporal evolution. But also, I think the recurrence is involved in this kind of convergence equilibrium idea, which is necessary for credit design, which you see in predictive coding. And you also see in other algorithms like equilibrium propagation and stuff in the literature, which kind of use a similar sort of style of tricks to achieve something close to backprop.
You're jumping ahead to my questions here I have about time. What is backpropagation through time, and why is it implausible in our brains?
If you have a temporal problem, you have this bigger issue of temporal credit assignments. You imagine an RNN, you have some weights in that RNN. Those weights are basically going to affect the computation going all the way forward through time, like step 1, step 2, step 3, step 4, etc. Because you change them in step 0, then step 1 changes, then step 2 changes. And so backprop through time is basically just explicitly tracking this change as it propagates through time. And so what it needs is you first propagate forward in time, and then you reach some output, and then you say like, hey, this output was good, it was not good, whatever. And then you need to store all the output through time, so at the end, you can then go all the way back through time to finally track down like what is the ultimate credit on the output on that specific thing you changed. And so obviously storing everything forward in time and then propagating it backwards in time is probably not something that the brain can do. In practice, this is a huge problem for people who actually do backprop through time as well, right? Like if they're really long temporal dependencies, then you just don't have enough memory to store all this forward and backward. And so in practice, people actually just need to cut it off. It's, you say like, I'll do 100 steps, say. And that's actually quite a lot of steps. But like I'll do 100 steps and then like cut off and do no gradients beyond that. And so that's also bad.
Okay, I've got a final question about time, and then I'll get onto some career questions. So I'm quoting you here. Continuous time also changes the problem the brain faces in perception from one pure inference to one of filtering. It must combine both sensory observations with prior knowledge of the current state to form its sensory percept. And in the quote, you also mentioned the need for filtering, which could be something like along the lines of Kalman filtering. And also earlier we talked a bit about this idea of memory, and you mentioned LSTMs. So there are a lot of open questions with all of these time issues, and I'm quite an interdisciplinary guy, so I'm thinking, what other areas could one take inspiration from to look at these memory time filtering problems?
Yeah, sure. So I think for me personally, one thing I've got a lot of inspiration for is actually the original engineering and control theory literature, where like these kinds of filtering problems and like Kalman filters and stuff actually come from. And so I think this is something that most people in machine learning don't pay much attention to, but actually people have spent a lot of time trying to think about these exact same problems and like actually integrating noisy sensory measurements and stuff together, which is something that like in machine learning, we don't really do that much. Like we have deep networks which like classify images and do like amazing things, but they're typically in this one-shot fashion. I give an input, it produces some output. And it's not like, I have some long stream of inputs and then I compute some long stream of outputs and maintain my state and everything. I think people especially don't pay as much attention to this as they should in reinforcement learning, where we have exactly this problem. You have an agent receiving a constant stream of inputs, and then it needs to do basically filtering to figure out the current state and then go forward. In practice, people just treat the agent as a feed-forward manner, right? So they say like the agent will receive some inputs now and then it has to figure out what to do, but without taking into account our whole history. And to some extent, this works because in reinforcement learning, you assume you have Markov decision phrases. And so the only thing that matters from the history is the current state, basically. But as soon as this fails, which it will do in any environment with partial observability, so you can't actually see the whole environment state, then basically you need to do this kind of filtering and take it into account seriously. So I think that's probably the main thing for understanding time. And I think this is something that most neuroscientists, most people in machine learning don't really think about that much. I also think time is ridiculously understudied, to be honest. Now, it's something I want to move towards working on as well, trying to understand how credit assignment works through time, because I think really in the last 5 years or so, we've gained actually quite a good understanding of how the brain could, in theory, there's no proof of any of this, but could in theory do some kind of different credit assignment algorithms on static computation graphs and static image classifiers and stuff. No one has any real clue about time at all. There's really not really that much work on it at all. And so this is a huge open area, and it's fundamental. The brain is not a static image classifier; it has to deal with time. And so how it does so is crucial really for understanding what's going on in the brain. As another point, to go back to what I was saying before, I just had a thought, which is that time actually makes some things quite a bit easier than space. Credit assignment through space is basically the alternative, is that time moves with computations, whereas space doesn't. And so if you think about you're going through a computation, in space, this is layers of a network, and so you need to go backwards, right? You need to go to the end and then come back to the beginning. But in time, by the time you've gone through the forward pass, you're kind of already at the time where you need to start doing the backwards pass, and so you've kind of moved with the computation lessons. And so that simplifies some degrees of credit assignment, but not others, basically. It simplifies credit assignment through time when you only have no credit assignment through space. But when you have both, then you basically get stuck again. So that's where I'm at with this anyway.
Okay, that's interesting. So is that sort of saying that the way of how quickly information moves from one structure to another structure in the brain sort of has to be analogous to the temporal aspects in the world? And if those are analogous in the sort of a productive fashion, then you can cancel out for time in a way by just the structure evolving to match that.
Yes, exactly. And like also that if you think about like you have some single neuron and like it receives a bunch of inputs and like gets a bunch of errors and then like updates itself slowly, then this neuron is staying in the same place. And so like you can basically integrate the information that it's receiving over time very easily. Whereas if this was a bunch of neurons, then to integrate all that information, you'd actually have to transmit stuff between the different neurons. There'd be different points in space. This is what I was trying to go for. And this is kind of the intuition behind how. So in normal automatic differentiation, we do backwards mode. So we go to the end of the network and go back. But there's also forwards mode, which is when you go from the start of the network and just go forward. And so time works very nicely in forwards mode auto differentiation. And because of this property, as long as there's no spatial interactions, as long as it's only purely temporal, then you can do it via forwards mode. But as soon as you get backwards in space and forwards in time, then things become messy again. And so that's kind of like what we need to try and figure out.
So I'll ask you like a few more career questions. And I'm quite glad I have you because a lot of my other guests are a bit older. So it's good to get like, how is it to pursue a neuro AI career these days opposed to 20 years ago?
Yeah.
So you did a bachelor in PPAL, so philosophy, psychology, and linguistics. And then you moved to a master's in AI. Was this sort of a difficult transition in terms of like learning the maths and the programming, or was that sort of natural for you? Or?
Yeah, I mean, I don't think it was intensive. There was an awful lot to learn, which I had no idea about. I don't think it was super difficult in that I don't think conceptually it's that hard. But I think there's just a humongous amount of material. If you go from like a sort of psychology or some non-mathematical, non-computation science discipline to then there's basically a huge amount of undergrad material you just need to learn, because the way computer science and especially maths work is it's very hierarchical in that stuff builds upon older stuff. And so then if you don't have a foundation, then you need to basically recreate the whole structure. Whereas in subjects like psychology and linguistics and stuff, it's much more sort of much less hierarchical in that there's like lots of different things, lots of different information, but it's not like there's much less of a like fundamental hierarchical core.
Well, you have basically started off with, you could call them soft science or more humanities directed to hard sciences in that transition. And I talked with Felix Hill about this as well, of like those two being very fruitful together. And I was just wondering, do you think, what is the right order in going about this? Because most people will probably focus on one of the two, but few people will try to do both. And then if someone wants to do both, let's say humanities, AI, and neuroscience, do you think they should start off with humanities in order to, because in my mind, humanities inspires you to think about lots of different like ideas, and well, like PPL is so broad, right? So you get lots of things you wanted to explore and you're like, oh, it's fine, but you don't know any of the maths or programming or like, as you said, sort of the hierarchical basis to build up upon that. So is it good to basically get inspired early and then learn the foundations? Or do you think it's good to learn all your foundations, right? Really get specialized in field. And then when you're maybe, I don't know, 30, 35, you finished a PhD, then get into the soft sciences by saying, well, now I'm going to start reading about linguistics and philosophy because I want to get inspired by these.
Yeah, so that's a really good question. I don't think there's a best way. I think it depends. Different people need to do different things. And I would always say that go for the stuff that like you find inspiring. And that's basically to get you actually motivated to do things, right? Some people can probably do this, but I can't like spend like years learning something you're not interested in, to have the far hope of learning something you are interested in. Like this is like something that it's really hard and you can't get, I can't get the motivation to do. I wouldn't recommend going that route. I think in terms of pure optimality, it's probably better to do the science and computational stuff first. But I think that like if that stuff is not motivating for you without the context of needing like I have these specific questions in like linguistics or like psychology I want to understand, then it's better to go for the humanities first and then switch back. People talk about like all the science stuff, and I was kind of doing that there where I was saying like there's a hierarchical foundation. It's like it's some hugely intimidating thing, but it's really not. The maths courses basically to get the foundational maths courses are basically just linear algebra, statistics, and like calculus, multivariable calculus. And so that's like 3 maths courses. And so like that's really not a lot. And year 1, maybe year 2 of undergrad. And then similarly in computer science, it's basically only a few real courses that you need to do. that doesn't take that long, and you can kind of do it in parallel with other things, is how I think. And I think that's probably the best way to do it, really, is to kind of do stuff in parallel, do mostly stuff you're interested in, but also do other things in parallel to try and build up foundations on the side. Because the key thing is essentially to be pursuing what you're interested in, but not to get stuck in this sort of region where like you want to do lots of stuff, but don't have any actual like skills to go and actually do it.
How do you manage writing so many papers, and do you have advice for people struggling with like workload, writing and publishing, because that's also quite time intensive?
Yeah, I don't know. That's a tough question. I just do things I'm interested in and have ideas and then like write them up. Learning to write stuff up has actually been quite a long process. And this is something you really learn. Like writing is really, really hard until like you've done a lot of it, and then it ends up being quite easy. Like most things, I guess. Like, it's important to realize that writing in specific genres is a skill. I'm very good at writing scientific papers now. I can write them quickly. Well, I don't know if they're good, but I can write them quickly. Writing quickly, let's say, is a skill. And so I've gotten quite quick at writing scientific papers. If I try and write something else, it's a nightmare. Like if I try and write, even just like write a blog post or something, that's like way harder than it is to write a paper now. But presumably for people who've been blogging for years and years and have like hundreds of posts, it's much easier for them. And then if they write a paper, it's like, so like writing is very niche and also like very specific. It takes such a long time to get into it, and just like writing a lot is like the only solution to that. The first papers I wrote, I spent like months writing. Now you spend like a week writing, maybe max. And so it's much, much faster.
So what about publishing? And maybe when you respond to this, what do you think what has been changing? So you're a postdoc now, and since you started with your PhD, has there been like have you noticed like a change in how you go about publishing? Or I mean, there's a case we made that in a lot of AI work that is it even good to publish? Should we just share findings in more efficient ways? Or what's your intuition about this?
Well, I'm really bad at publishing. Don't take my advice on this. I have so many papers which I like haven't submitted yet, and I need, and like other ones that I've got revisions to do, and I'm procrastinating for months. So like, don't do that. Be more efficient with that. I think it's important to publish stuff. I mean, in machine learning, obviously, it's the conferences that matter, not the journals. And so conferences are quite different. I like conferences because they have deadlines, so they actually force you to do stuff. Whereas journals, you can spend forever like, oh, it's not ready yet. And I do spend forever doing that, so that's not so good. But they have different trade-offs, right? So conferences obviously much shorter, more stressful, so kind of hectic, and they have these deadlines. They're also quite harsh in that they'll just reject you. They'll be like, no. Whereas journals will often be like, how about you do all these revisions and then maybe? And so it's actually quite nicer in that sense. Whatever neuroscience or machine learning, publishing is important. Personally, I don't think it's that important for like getting your stuff out there. I think archive, like everyone basically reads archive stuff. I don't know anyone who's like, I will only read this if it's paid in a journal. But it's important basically for career reasons, and that people will look at it essentially. But on the other hand, like if you don't want to do career stuff, if you just want to get a PhD, you probably need like one publication, I think, for a PhD. But if you have that, and then you just do the rest in archive, that's also fine. If you know you're going to not go into academia, but like if you are, then you should probably try and publish stuff efficiently.
Yeah. Final question. What future projects do you have planned? And I probably realized that you'll have 20 ideas. So what's the project you're most excited about, or sort of the domain you're most excited about?
Yeah, okay. Well, I have many I have many projects planned. Okay, so let's split this up into a couple of things. So basically the three things I'm excited about are, one is continuing on the stuff with, I'm trying to understand how credit assignment and predictive coding and all this stuff works. I'm trying to understand to what extent can like new versions of predictive coding actually work and be sort of implemented in the brain. And so we've got some very exciting stuff about how predictive coding, because previously my work was on how predictive coding approximates backprop. And I now no longer think the brain does approximate backprop. I think it does something else. And so we have some interesting work now on like when predictive coding doesn't approximate backprop, what is it doing? Because we've shown that it can still actually learn and can actually still like train neural networks and stuff, which is really cool. So I'm working on that and trying to also understand like the theory behind that. So that's number one. Number two is related to the stuff we talked about regarding sparsity. And so this is something I haven't really done anything with yet. I plan to, hopefully, in the future. We'll see if I actually find anything interesting. I have some interest because this is also related to my other work, which we haven't talked about here at all, which is about like on understanding associative memory models. So like I had a recent paper about like universal Hopfield networks and stuff, and I'm still trying to understand how associative memory, what that is, and how that relates to sparsity. And I think there's a big relation. And basically, my personal feeling is that sparsity is useful for memorization and quick learning, whereas Lack of sparsity, dense learning is useful for slow learning, but more generalization. So that is what I think the trade-off is, but that's pure speculation on my part. So I need to actually try and figure out whether or not that is actually the trade-off and understand that, and then how that relates to different architectures in the brain, like the cerebellum we talked about, the cortex, the striatum is also highly sparse in this interesting way. And so like things like that. And then thirdly, the other thing we talked about is the temporal credit assignment. And so to me, this is really the fundamental thing, right? So like, because the brain has to do temporal credit assignment, and it does it pretty well. Like people are pretty good at learning long-term dependencies, and we don't really have any good understanding of how this works. And so if we could solve temporal credit assignment, then I think we'd be getting pretty close to how learning works in the brain, which would be amazing. So that's sort of the long-term three things I'm working on.
This has been really interesting, Beren. I really enjoyed the chat. Thanks for having this chat with me. Thank you.
Oh yeah, no worries. It's great to be here and chat with you.
I hope you enjoyed this episode. The next 2 episodes coming out will be about linguistics and natural language processing. We will have Felix Hill from DeepMind and discuss his work with grounded language models, and Alex Laskaridis from Edinburgh, who will tell us a bit about her work on logic, discourse and gestures. To find out when these episodes are coming out, follow the Twitter or LinkedIn account in the description. Enjoy the rest of your day.